All right, guys, I think we're going to go ahead and get started. So thanks for everybody for tuning in. So hey, everybody, welcome to ARE Live. I'm Mark Tier, the founder of Black Spectacles, and today we'll be talking project development and documentation, PDD. Using a mock exam, we'll cover a variety of topics in this particular division of the ARE. And then after, you should have a good understanding of some of the concepts that you'll need to, let's say, be competent in as you move forward in trying to pass the PDD exam. Before we get started, if you'd like to attend our next ARE Live broadcast, where we're going to discuss why and how the questions on the ARE are written so that you're prepared to own them on test day. So you can imagine that it's actually a science. We've been spending a lot of time learning about this here at Black Spectacles. The way in which questions are written is actually a specific science. And what we're going to do is we're going to have our Black Spectacles question writer and resident architect, Heather Rivera, explain the 5 different question types you'll see on the ARE. She's going to dive into why they exist and some of the best ways to efficiently attack them.
And let me just say that I think that's a great approach to get yourself to the point where you just feel comfortable with the way the questions are coming at you, so you can really just focus on what's the attack. Right?
Yeah.
It's a great way to approach the process.
Yeah, it's crazy. Some of the words we've learned is distractors, right. The stem of the question. Like there's actually like
a whole process
there's
to
language,
putting these things together.
Yeah, there's language for how you actually create questions, which I never knew anything about. And actually, once you kind of know that, if you had sort of that filter or that lens through which you could see the questions, they don't seem maybe as random as they are, and also probably help you find the right answer. So that should be a great session, and of course, in addition today. So in terms of updates to our products, you may have heard that we're the first ever NCARB approved test prep provider for all 6 of our ARE study materials. So that's all 6 exams. Of course, it covers our lectures, our practice exams, and the flashcards. In addition to all these, we of course have our group coaching program, and which we just closed. We're about to kick that off. Again, man, that program is growing really rapidly. So if you would like to essentially, find a group of, or I should say get paired up with a group of people who are very serious about taking the exams, and you work with a coach. They keep you on track over the course of about 6 or 7 months. You'll take all 6 exams. It's probably the fastest way and probably the funnest way, most fun way to go through this process. We have our next cohort is in May, so you can join the wait list for that. And I always like to say, if you'd like your boss to pay for your Black Spectacles membership, be sure to tell them about our firm licenses. Whether you work at a 10-person or 10,000-person firm, we have a firm license that gives multiple users access, group administrative capabilities and reporting and all that stuff. So you can go to blackspectacles.com/firms to learn more about that. For those of you who don't think your boss there's any way he's going to pay for your Black Spectacles license, well, good news, we have a special discount on individual memberships today. We'll share at the end of the show. My guest is Mike Newman. If you don't know Mike, he's a senior lecturer at the School of the Art Institute of Chicago. He's also the founder of Shed Studio, and he's the instructor for our Black Spectacles online ARE exam prep lectures. If you haven't already checked those out, you can go over to blackspectacles.com to watch any of those free tutorials from the courses. And then today, we'll be taking questions using the GoToWebinar question box. And for all of you who actually submitted answers to the mock exam, you'll be entered to win a free 1-month ARE prep subscription. And additionally, those of you who got all the questions right, which we're going to be tracking during today's session, you're going to get a free Black Spectacles t-shirt. So with that, I'll hand it over to you, Mike.
All right. Thanks, Mark. So as everybody knows, project development and documentation is I like to think of it as the 5th in the 6 series of exams. Mm-hmm. So you've got the practice management and project management as sort of the first 2, and then you've got the analysis one, which is kind of like pre-design and all the things from surveys and looking at a site and the initial client meetings, things like that. And then the next one, which is really about essentially the version, the PPD one, is essentially the version of schematic design and beginning of design development. And then this one, PDD, is set up so that it's kind of taking you from design development through CDs, getting you ready for construction, kind of moving into that documentation phase and sort of final design choices. And then eventually you'll get into the evaluation, which is effectively the construction administration version of the exam. So let's just dive right into this. We're going to sort of jump in and do a couple different questions that just sort of give a little taste for the sorts of things that can come up onto an exam like this. These are just fairly simple questions that are meant so that I have certain kinds of topics to talk about. These are not sort of perfect reproductions like we were just talking about the science of writing these questions. These are really meant to sort of set forth a series of topics for us to talk about. So don't take these as direct scientific ways of approaching the questions, more just sort of topics for us. All right, let's dive in. Number one, what is the footprint of the stairwell for a typical switchback stair in a small hotel you are designing if the floor-to-floor height is 11.6? So first thing to note here is be careful on these things. Often you'll see something where it talks about the floor-to-ceiling height, and while that's useful for lots of different design aspects, it's not what you would need to understand a stair. Stair has to be floor-to-floor. That's an easy mistake. So this one is floor-to-floor, so that should be pretty good. First thing I'm going to do is change 11.6 into inches. So that's 138 inches, I believe, just because it's going to make it a little easier for us to analyze. And then we're going to take a quick look at the answers. So A is 15 foot by 6 foot, B is 18 foot by 9 foot, C 15 by 9, and D 18 by 6. Now, anybody that has actually put in an egress stair into an office plan or hotel plan or anything like that will probably recognize pretty fast, and I'm just going to jump to the quick on this one and just say the largest one here is going to be the answer. It's going to be B, 18 by 9. And we'll come back to why that is. But if you can answer a question like that and feel very confident, more power to you. If you can't, then what you're looking for here is, well, how do I quickly figure out what the issues here are? So in order to understand how big the footprint of the stair is, I'm first going to need to figure out, well, how many steps do I have? So this is why we figured out that 11.6 is equal to 138. So my first step is going to be saying, all right, 138 divided by 7 inches. And the reason I'm dividing it by 7 is because that's the maximum accessible riser height that I can have. So when I do that, I'm going to end up with, I don't remember the exact, but it's 19.7 something. Doesn't really matter. It's right in that range of 19 point something. You can't have a 0.7 riser. That wouldn't make any sense. It would be a death trap. People would trip on it all the time. So we immediately round up. And we're going to round up, so that's going to be 20 risers. Now, just sort of interestingly, I can then go back and say, all right, 138 inches divide by 20, and that's going to give me 6.9 inches. So that means each riser is 6.9. That's interesting. I actually don't need to know that for this to answer this question, but there you go. So main thing I'm figuring out here is I've got the 20 risers. So we start looking at a footprint of what the stairwell is going to look like. And you could actually draw this out if that was useful to you on your scratch paper, or just kind of do it in your head. None of this is particularly complex. So here's my my stairwell, and if I put a couple of dimensions on here, that dimension is going to be a minimum of 44 inches. It's possible in certain municipalities that might actually be 48 inches. So both of those are possibilities, but typically 44 inches is considered the minimum egress stair width. So I've got 44 and 44, and then whatever space in the middle there. So I'm roughly around 8 foot at a bare minimum, and much more likely to be a bit wider than that to give a little room for the railings in the middle. So right off the bat, before I've even done any real thinking about it, I can say that the 6 foot wide and the 6 foot wide can't possibly be the right answer. So the really only questions here, the only question left is it the 15 foot length or the 18 foot length? So let's figure out a couple of these things. So I've got the 44 inches there. And then the question is, how big is that? Well, we have the 20 risers, which means we have 10 risers on each side. So we're going to go through, put those in. I'm not actually counting there, so I'm just kind of putting them along. And the one thing that we quickly realize is that if we have 10 risers on each side, that means we have 9 treads, because there's a riser at the top and a riser at the bottom. So each tread is going to be 11 inches. So that means our total run there is 99 inches. Again, that's because it's a standard accessible stair is going to be a 7-11 stair, where it can't be more than 7 on the riser and it can't be less than 11 on the tread. Now, interestingly, if you actually look at the treads, the sort of classic accessible stair is going to look something like that. Not very well drawn, but you get the idea. So there's the 11 inches, but typically I actually get another little inch or so back underneath there. So the actual tread dimension is usually about 12 inches, but if you're looking at it from a plan standpoint, it's 11 inches clear because that other little angle gives you just a little bit more space for the toes. And the reason that you do that angle and not the sort of old school version where you have a little lip like that is that little lip, if you imagine somebody coming up with their boot, somebody with very thin ankles wearing a boot, that little spot right there becomes a trip hazard. So from an accessibility standpoint, these sort of angled risers are sort of more typical. And there's a few other ways you can do it, but the sort of classic is that angled for like a concrete stair or something, or steel stair. So we have the 11 inch, we have 99, that puts us there, 44 and plus the 99. If we sort of compare 18 foot is going to be, what, 216 inches, I believe. 15 foot should be 180. If we start adding those things up, we'll realize that we would only, for 15, if we subtract 180 minus 99 minus 44, we're only going to end up with about 30-some inches for this entire landing, where our door needs to be, where the travel path needs to be, where potentially you might have some other requirements of areas of refuge and things like that. And that's just not enough dimension that's left. So the 15 foot can't be right. It must be the 18 foot. So that's why we got to B. So that's a lot of drawing and figuring it out. But remember, all you're really thinking is, all right, well, how big is a stair? 44-inch minimum. Do 2 44s. That's we're at almost 8 feet. We obviously, so we cross off the first two, A and D, right off the bat. And then it's just a matter of kind of, well, how big would it be? So I've got roughly 10 risers on each side. That gets me to 99. Like, you can do all that in your head without having to draw it out. We just drew it out so you could see it more easily. So the answer in this case, B, 18.9. Again, these kinds of questions are set up in order to be a simple question, but it's a simple question that requires you to sort of understand the gist of how stairs work and sort of important key accessibility dimensions, 711, 44, how the risers work when you start adding them up. So the thought here, like, they're not trying to trick you, they just want to find out that you can kind of grasp the gist of how a general stair works.
I think that makes a lot of sense, and I think just as a reminder, man, there can be so many sort of little details about stairs. These guys are testing again. Remember that famous T-shirt we still haven't made yet. They're testing for minimum competency, not for like
design
the
excellence.
gnat's ass.
Or,
like,
yeah.
So they're looking for a simple answer here.
Yeah, you're not looking to prove that you're the most beautiful designer ever. Like that's not the point. So yeah, other issues here. The travel path you could imagine being an issue. The railings, you'll note that railings always go beyond the risers. They go a foot past on either side, including getting the angle full down to the correct height. So the footpath can actually often be close to 2 feet past by the time you have the angle going. Those kinds of little issues, those are things you should know in order to be able to answer simple questions like this.
All right, we're down to 181 people are still in the running.
All right. Number 2. In the bathroom, which specialty electrical outlet would likely be appropriate? So we have 4 possible answers: waterproof, VAV, GFCI, and arc fault. Well, first thing we can do is we can cross off VAV, because that's actually a HVAC system, not an electrical system. And then the question becomes, all right, well, what about waterproof and GFCI and arc fault? Well, I'm going to talk about arc fault for a second. Arc fault is sort of an interesting specialty outlet. Many of you have probably come across it in the last few years. The arc faults have existed for a long time, but they didn't really become requirements until relatively recently. And there's a bit of a backlash from electrical engineers and various other folks about whether they're truly helpful in the process or not. But the concept of an arc fault is that it deals with static electricity. And the trouble with static electricity is if you have static electricity buildup near an outlet, you can get what's referred to as an arc, right? So if you imagine Frankenstein, where you've got the 2 poles on either side of his head, and there's that sort of a little lightning bolt that goes between them, that's an arc, right? That's an electrical arc. And so if you get a static buildup and then there's an outlet there, you can get that electrical arc, that little lightning bolt that goes between them. And if there happens to be linens nearby or curtains or something like that, it's a big fire hazard. And so there's been, in recent years, most of the codes have picked up having arc faults in bedrooms and potentially in living rooms, places where people might be sleeping is essentially the way that's always been explained to me. I don't know if that's the technical response, but that's the way it was always explained to me. And so the arc faults do a very serious job. But like I said, there's been sort of a pushback about whether they're actually effective in saving any lives and or saving fires. So it's a bit of a up in the air thing. It's hard to know how it would show up on the exam, but it is a real and potentially quite important electrical device that you should know about. But that's not the issue in a bathroom. I suppose it could be an issue in a bathroom, just like it could be an issue anywhere, but much more likely a bathroom issue is going to be about water. So that leaves us with waterproof and GFCI. GFCI is ground fault circuit interrupt. You might see it referred to as GFI, ground fault interrupt. The difference between the ground fault interrupt and the ground fault circuit interrupt is that the GFI is just located in that outlet. And so it's just there in that one box. The circuit interrupt means the entire circuit that's on is on the ground fault circuit interrupt. A GFCI is set up so that when, let's say you have a hair dryer and you're plugged it in across on one side of the sink, but then you're using it on the other side and the cord goes into the water and there's a little break in the cord. And suddenly electricity can find its way out of the wire and into that water. And in the meantime, somebody is brushing their teeth and using the water and touching the water. And that would be a huge disaster because now the electricity has multiple places to go. It's not just following the path of the wire, it can go anywhere. And so a huge surge of electricity, because it can go anywhere, will go out into that water. Well, the GFCI can feel that. It understands that there's a weird and there's no reason why there would be this huge sudden surge of power, and it cuts the power off before any damage can happen. A waterproof outlet is in fact a GFCI or GFI outlet. So GFCI is the category that says this is the device type. Waterproof it's not only that, but no water, like it can live outside and in a very, very wet situation. And it has covers and things like that. So the answer here is actually the GFCI. The waterproof is a potentially good answer. It's just that most people, very, very rarely would you actually put a actually truly waterproof outlet in a bathroom, because it gets wet. It just doesn't get that wet. You'd use a waterproof in a situation where it's going to get rained on, or where it's right next to a pool and water is splashing up onto it, or something like that. So the waterproof is much more expensive and much sort of heavier duty. The GFCI is sort of everyday water locations. So the places that you would see that are going to be bathrooms, it's going to be the kitchens, it's going to be laundry rooms, all of those. Basement spaces, just because you might get just enough water in those basement spaces and moisture. So any place you think there's going to be water, but not water literally coming at the actual outlet all the time. It's more that the cords might be in places that are going to get wet. So this is one of those ones you should absolutely know. Make sure you feel very comfortable with GFIs and GFCIs.
All right, down to 171.
Okay, this one's a little bit odd. This is sort of a classic old school NCARB type question because they're expecting, it seems like such a simplistic question, but they're actually expecting quite a bit of sort of foreknowledge to really be able to answer it. So the question is, if the intention is to be efficient with the steel and keep the overall depth of structure low, which steel framing layout would likely be best for a small 3-story office building? So the first thing we can say is, when we look at these 4 different options, 2 of them are clear spans. One, A, is a clear span for 120 feet. D is a clear span for 90 feet. Well, those are pretty serious clear spans. There is very little chance that a clear span is going to be the efficient and shallow depth structural system for this building. It's also just would be unlikely. Why would you do a clear span? Now, there are some famous classic examples of buildings, office buildings, that have clear spans. The Inland Steel, for example, has a beautiful clear span, and it means you can stand in the middle of those spaces and look out the windows all the way around. There's no columns in the way, and it's awesome. But it's not typical. It's not the way you would normally do it, and it's certainly not an efficient way to do it. Those clear spans would be very, very deep. And it would also, for an office, probably be a little bouncy, but that's sort of beside the point. So our real choices here are between B and C, and they seem very, very similar. They're both 30 by 40 foot bay systems. And the 30 by 40 foot is very specific because the sort of sweet spot for steel is going to be right in that range. Sort of classic steel spans are, 30, 35 feet, 40, 45 feet, kind of right there. Maybe down to 25 might be still pretty efficient, possibly up to 45. You can span all sorts of distances in steel. You could span 10 feet in steel if you wanted. You could span 50 feet in steel. It's just that you're losing the sort of straightforward efficiency numbers once you get lower and higher than these. So that's why you'll see most of the time when you look at a steel framing plan, and it's pretty typical that the numbers will be in that kind of 35, 40 kind of foot range, because that just is where it economically makes the most sense. So now the difference we have between these is in the direction of the steel. So I'm going to do a quick little nomenclature thing here. With framing plans, it's always decking to joist to beam to girder to column. Now, you don't always have all of those. I mean, presumably you have decking, but you don't always have joists. Sometimes it's just decking from beam to beam. Sometimes you have joists and beams, but no girders. But that's the order that you would talk about them as. So a girder is going to hold up multiple beams. A beam is going to hold up multiple joists or straight to the decking. The joists are going to hold up the decking. So when we look at these two plans, we can see that on B, we've got the girders running across, and then we have the joists running from girder to girder. On the C plan, we've got the girders running up, down, and the beams running from girder to girder going across. So the difference here is, if you think about this sort of order of operations of the kind of how the load is working, the girder is carrying more load, right? It's carrying multiple beams worth of load. The beams are carrying less load. So in the C version, I have the thing that's carrying the most load going the longer distance. So in order for that to really make sense, and this is going to be sort of a terrible little drawing, but hopefully it'll be clear. That means that the girder is going to be pretty sizable, whereas the beam, which is only going a short distance and also already has less load on it anyway, so the beam to girder relationship, the beams are going to be much smaller than the girder, and the girder is going to be much bigger because it's spanning farther and it has more load. When we look at that same situation in the B scenario, where the girder, the one that's taking more load, is spanning a shorter distance, and the beam, which is taking less load, is spanning the longer distance, then you can usually get it to look something more like that, where the beam and the girder are roughly the same size. So you're essentially making the beams deeper, but you're doing that and that's allowing the girders to be less deep. And so from an overall standpoint, it's a little hard to tell with this angled line there, but the thought here is that the whole thing is actually less deep of a structure and more even across the board. So the classic answer to this is going to be B. That's sort of the famous ways that the girders go the shorter dimension and the beams go the longer dimension. Now, when you actually get into a real design with real information where you have other sources coming in here, you may have all sorts of things that would push you one way or another. It may be that having no columns is better, and so you're going to just deal with the deeper section. It may be that the way that the ductwork is going to go, it'd be better to go with C instead of B. It's all sorts of things that could impact these choices, but the only thing we know is this desire to have the overall depth of structure be lessened, and the way that you're going to do that is by having the elements that take the most load have the shorter spans. So that's why we're ending up with B. One quick comment on this is that there's a weird thing that happens with discussions about steel. When you talk about steel, people talk about efficiency, and when structural engineers talk about efficiency, and this then sort of seeps over into this exam, they almost always are talking about using less steel, less weight of steel, and therefore less cost of steel. So just as a quick reminder, if you think of like, let's say a W21 by 40 or something, I'm making that up. I'm not even sure if that's a real size, but it's roughly similar to a real size. That would be a wide flange. That's what the W means. And then the 21 is the nominal depth, so 21 inches tall, roughly. And then the 40 would be pounds per linear foot. If I can do that if I can do the same span with, let's say, a W24 by, again, I'm just making these numbers up just to to be illustrative, by 38, which I don't think exists, but let's say it did. That 38 is less weight of steel per linear foot, but it's a taller member. It's a deeper member. So from a structural engineering standpoint, this would be the correct answer for how you make it more efficient. But interestingly, if you actually are thinking at it like an architect, it may well be that the overall cost efficiencies might actually be better with the more shallow structural member. If you realize that there's now on each floor a few more inches of brick and a few more inches of concrete and a few more inches of heated air from the HVAC system and a few more inches of glass mullions and whatever it happens to be, there's sort of a competing idea of efficiency. So I say this not to confuse everybody. I say this to just say, be a little careful about how you think about steel. When we talk about it on the exam and we talk to a structural engineer, they are almost always talking about weight because weight equals dollars. From your standpoint, that's an important consideration, but so is height, and so is clearance, and a whole series of other issues. So let's move on. Okay, number 4. Tenants of a large residential building are complaining that they can hear each other's phone conversations, and your team has been called in to help fix the situation. So people are hearing from one unit to another through the demising walls. Where are you likely to first look for a way to make this situation better? And our answers are phone outlet locations, so like we could put the phones farther away from each other. That is such an old school answer, I can't even believe it. Most of you probably don't even have an actual phone, like a wired phone. But conceptually you could have the phones be farther away from each other, and that would be helpful. The IIC assemblies, C would be the wall assembly to get a better STC. D would be the NRC ratings of finished materials. So let's digest a few of these. So IIC is going to be the insulation impact class. So that is a viable answer for thinking about sound between units. Typically, though, when you're talking about IIC, not always, but typically what you're actually talking about is the impact sound of somebody walking on a floor and the sound of that impact coming through to the unit below. There's a bunch of other similar things that it can be referring to, but that's sort of the classic. For example, somebody walking around in high heels and you have that kind of intense click sound, that is translating through the materials in a very specific way. And so the IIC can help you deal with that and sort of understand what those numbers are. That's not really what this is talking about, though. This is talking about phone conversations. Well, let's look at the NRC. So the NRC, the concept of the NRC is the noise reduction coefficient of materials. So the classic version of the NRC that you would be using, and probably many of you have used already, and you just may or may not have realized it, is you're in, say, an office space, and you're going to put up some ceiling panels. Well, those ceiling panels all have very specific NRC, and the idea is that the sound that's in a room, right? So I've got a room, and I've got people standing in that room, and other people trying to work in that room, and various things happen, and these people are chatting, and so their sound is bouncing off the ceiling and coming down and bothering the people who are trying to get some work done. Well, if this ceiling is made out of a material that has a very useful NRC rating, then quite a bit of that sound is just going to get lost up there in that ceiling in the little crevices and get absorbed into the material, and so very, very little of it will actually come down and bother the people who are trying to work in the room. So NRC also very useful in thinking about how to maintain a reasonable amount of sound in a room, in a space, but doesn't really have that much to do. It's related to and has something to do, but doesn't have that much to do with the transmission of sound from one room to another. When you have two rooms next to each other and you're worried about the transmission of sound, so I've got something that's making sound on one side, say a drum, and it's making sound over here, and that sound is going through that wall and then finding its way into the other space. That is about the STC ratings. So that's the sound transmission class. I always get the C class and coefficient mixed up, but I'm pretty sure it's sound transmission class. And so the answer here is going to be C. And walls with pretty terrible sound transmission numbers are going to be down in the kind of high 30s, like a 38 or 39. Ones with really high might be up in the high 60s, something like that. Sort of typical for a demising wall you'd be looking for would be somewhere in the high 50s up to 60 in that range. And the STC ratings are kind of interesting. They're really focused on understanding the transmission of the pitches of most human voices. And the reason for that is those are the ones that are really irritating to people. If you can hear half of a phone conversation, it drives you crazy. So they're really aimed at that. And the reason that they're aimed at that is because if you actually tried to make a wall that could block out all sound, it would be very, very difficult. Like think of all those times you're outside on the street and you hear a car coming and you hear that bass from somebody listening to music and you're thinking, God, is it only bass? What's going on? Well, that's just the pitch that's getting out of the car. The rest of it's being contained in the car. Well, this same kind of situation, if you actually had somebody banging a drum on one side, having an STC rating of 58 isn't going to do much. That drum sound is going to go through, but it's also not going to bother you as much because it's not going to engage your brain in the same way that being able to hear somebody's conversation would. So it's good to get to know these different terminologies, IIC, STC, NRC, and how they sort of work, because it is likely you're going to get some acoustic questions somewhere on the exam, specifically on PDD.
I think we're down to 111.
Way to go.
So
it's pretty good.
Yeah, we're doing pretty good.
All right, number 5, you're doing a strip mall, so similar kind of use. And the question was for a DX RTU, why would somebody be using a DX RTU for your strip mall? So the RTU means rooftop unit. I love how simplistic it is. Like you always think, oh, RTU, that must be some really like intense, deep, highly technical term. It just means there's something sitting up on the roof. It's a rooftop unit. So that's an HVAC unit that's sitting up on the roof. And the DX means that it's working with refrigerant, and the refrigerant is directly part of the transition of heat or cooling from the refrigerant system into the air that's being blown into the space. So there's no chilled water loop, there's no secondary system, it's just directly working with the refrigerant. So most RTUs up on the roof are DX, and the question becomes, why would we put DX RTUs onto a single-story strip mall? Imagine, I don't know, like a 7-Eleven or something like that. Like, why would you use that kind of system? What are the 3 things out of this list of 6 that would make that make sense? Well, one reason I might want to put my HVAC unit up on the roof is that's going to mean that the noise is not in the unit. The noise is now up on top, right? That you still have the air coming down through the roof into a little duct system, but you don't have the noise that machine, the big fan, all that stuff. You're putting that up, and maybe you're bothering your neighbors, but you're not going to be bothering your clientele on the inside of this space. So that's one answer. Another good answer here is doesn't take up any floor space. So that whole mechanical room that would normally have an HVAC unit sitting in it suddenly doesn't have that in it anywhere because that whole room is gone because it's all sitting up up on the roof and not taking up any indoor space. Now, if you're somebody who's is like a developer and you're building this thing and then you're putting this stuff out as a rental, well, that's super handy, because what that means is you're not like losing any of that square footage. You get to rent it all. So very typically simplistic buildings like strip malls, it's a simple, straightforward, easy way to do it. So we have one more potential answer. The thing here says easy access for the standpipe. Well, standpipe's actually about fire protection. It's the way that you get water into a sprinkler system. It's not related to a DXRTU at all, so that's not it. More durable and long-lasting. So let's take 2 seconds and think about, if we're going to put a delicate piece of HVAC equipment up on a roof in Minneapolis that's getting snowed on and sleeted on and heavy winds and hot sun in the summer, like, that is absolutely not going to be more durable and long-lasting. In fact, it's pretty short-lasting. But so are most strip mall units. Like you get somebody who stays in that space for 5, 8 years. That's probably pretty good, and those systems will certainly last that long. But it would be way more durable and long-lasting if you had it in a basement or inside in that space. So it's definitely not D. That is one of the big problems for RTUs, is that they are not durable and long-lasting. How about E? Off-the-shelf quality can be easily replaced and therefore makes for good flexibility. That's absolutely true. One of the great things about having on a simple one-story building like this, having a RTU, especially DX RTU, is that it's all sort of self-contained. And if that client goes out of business and a new people move in and maybe they take over 2 spaces or something, it's very simple and straightforward to be able to add these things. It's not always the easiest to put a big heavy piece of equipment up on the roof, but conceptually it's simple and flexible, and you can just take one off and put another one on that's bigger and more powerful. And so that off-the-shelf quality allows for pretty easy flexibility down the road. And you'll see a lot of these things where the developer, the owner, will actually build the building, build the shaft, build the position for where that RTU is going to go. And then when the tenant comes in, they put their own unit in, so that they can then adjust it to their specific needs of what's going to happen on the inside. So it's very flexible from that kind of standpoint. This is a great way to go. Then the last one, by placing in the basement, which we've just said, RTU means rooftop, so that one is definitely not the answer. So A, B, and E are the 3 answers for this. So this one was all about what the heck is a DX RTU, and why would I want to put it on top of a one-story strip mall building.
Like, going back to question 3 here, Brian had asked, how are we supposed to know in that diagram what's a beam versus what's a girder and what's a joist? Because there's diagramming language there almost that we're using.
No, absolutely. So what I was saying over here is that the terminology always goes in this direction, and I say that only. With steel, the difference between joist and beam gets a little slippery. For me, I almost always think of, if I see a wide flange, I think of it as a beam. If I see something like an open web joist, I see that as a joist. However, if you're talking to structural engineers, they will often jump back and forth that a wide flange can certainly be a joist. So it's a little bit of a slippery thing, and I don't mean for you to overly worry about it. It's just that decking spans from joist to joist. If there aren't joists, if you only have beams, then the decking is spanning, it just goes to the beam, and so it's spanning from beam to beam. And so that tells you which direction the decking is going. And then the beams span from girder to girder, but if you can do it without girders, then there's just beams, and so the beams are spanning to columns or to bearing walls or whatever it happens to be. But if there's something that's picking up a girder, something that's picking up a beam, that's a girder. That's the definition. So when we look at those 2 drawings, and so I'll just do one more time. So in C, that girder right there is picking up the load of this beam and this beam and this beam, etc. So just by the diagram, you can see which one is a beam and which one is a girder. whether you decided to call the beams joists or beams, it doesn't really matter. It's still picking up that's the only one that could be considered a girder.
Okay, and then a different Brian asked, the question asking to be efficient with steel, wouldn't making all the beams bigger be less efficient than having just the girders be deep?
Well, the actual answer to that is typically no, which is interesting, but that's sort of a long question. The main thing here is this very specific question of keeping a low overall depth. That one is really the driver of the question, and so by allowing the beams to get a little bit deeper, you're reducing the size of the girder, which means the overall structure is actually significant numbers of inches smaller.
Okay. All right. Well, thank you guys for those questions. Thank you, Mike. For those of you, if you'd like to attend our next ARE Live podcast, where we'll be discussing the 5 question types and sort of how they're composed, sort of the science behind them. I just posted a link in the chat box in your GoToWebinar control panel, so you can go there and register right now, or you can just go to blackspectacles.com/podcast and you can register there as well. To learn more about our ARE exam prep curriculum, you can go to blackspectacles.com, where you can try out any of our free course videos. And if you would like your boss to pay for your firm membership, or for your membership, be sure to visit blackspectacles.com/firms to learn more about our firm memberships for firms of any size. I mentioned a discount for individual members, so for those of you who are ready to start preparing for the ARE right now, you can use coupon code PDD22119YT to get a 15% discount for the entire duration of your ARE exam prep membership. And then finally, for everybody, tomorrow we'll send you an email follow-up about today's live broadcast, so please let us know what you think. Share any suggestions you may have. I promise we do read everything that you guys send us, and we use that feedback to tune our next episodes. So thanks for tuning in.